Thanks, everyone. It's a great pleasure to visit IPAM. There are certain things that maybe in NVIDIA we do that we cannot talk about. But today, I think maybe I'm going to speak on from the perspective of the scientist to talk about what I think will be maybe the most critical innovation or things we can do in the next couple of years to really enable AI to make groundbreaking contributions in science. So I'll be talking more about world models. So today's program, we have already been hearing lots of instances of world models, like this morning, Hayden's discussion, and also in the previous talk, Huifeng's discussion about how we can simulate what happened in the biological experiments. But I want to dive a little bit deeper into this. So the motivation is that we have been observing in development of LLMs, for example, in math and coding. Generally, if the answer is easily verifiable, then we see very rapid progress. When answers are not very easily verifiable, we see actually pretty slow progress. So if we follow this rationale, then for scientific discovery, ideally, if we can get feedback really fast in a scalable manner, we'll be able to make discoveries faster. So generally, the question we want to ask is that suppose I change the design variable, control variable, different treatment, what would happen to the outcome? There has been lots of work in the past in terms of simulation in many different fields. Many fields actually critically rely on simulation. I'm listing a few. We also think about like other important industrial domains like chip design. That's also extremely critical. So I want to somehow mention one point that maybe in the era of AI, there could be something sitting in between the wet labs and traditional simulation. So basically, in traditional simulation, there has been lots of efforts dedicated there to optimize the overall computation and building the physical models. Generally, they require full specification. You need to write down the full state, noise, the distribution, boundary conditions. Then we have a very precise mathematical equations governing the evolution of the system. But generally, if we go to another extreme, like we are conducting experiments in wet lab, and many things are underspecified, partially observed. Actually, there's also a general issue of reproducing the experiments done in wet labs. So one point I was thinking is that there actually could be one approach of working in the middle. So basically, we can try to apply what we learned from the beta lesson to simulations to try to absorb the underspecification into latent states by fitting to real outcomes. In some sense, it's way cheaper than real simulation, but also not as expensive as the wet labs. Of course, the devil is in the details, so I think there has been lots of exciting projects going on for these directions. It will be very exciting to see what we do in all the different directions, and also whether it's possible to have a unified view towards this general problem. So what generally do I mean by world model? We consider this to be a generative dynamic model that supports intervention queries and calibrated uncertainty. Two features I consider to be quite important for the system to be very useful. So in terms of intervention queries, basically the world model needs to be able to predict what happens to the next state and also the observation, conditioned on the current state ST and also the actions taken by the agent. So basically, agent could take arbitrary actions, maybe actions very hard to take in real wet lab experiments in particular states that also very hard to reproduce. But the world model is supposed to accurately predict what actually happens for the next state in evolution. And then we can actually roll out the whole sequence given different configurations of action sequences. At the same time, ideally, the world model should be able to tell us how confident it is for predicting the next state and also next observation. It's very critical because it's very different from traditional simulation. We are really unsure about its outcome prediction in many cases. Ideally, if the model is able to tell us it's really unsure about certain predictions, we can actually conduct real experiments in that setting to collect real data so that next time the model can actually calibrate its predictions better. So basically, the very important issue is that when we are doing extrapolation, we need to make sure we understand the corresponding uncertainty so that it really guides the experiment design in the future. Borrowing from the insights we gain from coding, from math, in particular in terms of formally verifiable math, if we're able to achieve a closed-loop science, which I do believe that many companies are trying to move towards this direction, then we really have the potential to significantly accelerate the speed of scientific discovery. So basically, this problem has been there for a very, very long time. In the past, we have been talking about sim to real gaps for many different scientific domains, like in robotics and autonomous driving. And recently, we have been observing that even in those domains, the capability of conducting really realistic simulation has been significantly enhanced by adopting AI. Actually, considering NVIDIA's technologies like DLSS and also Omniverse, they are actually also very good examples from this perspective, and there are also actually many more examples. It would be actually very nice to also have a unified view towards all these different applications, so that whenever the world model predicts something, then we are confident it's actually accurate with a very calibrated uncertainty quantification. So once we're able to do that, actually it can really accelerate the scientific discovery and experiment design. For example, here in last equation, we're really talking about two things. So one thing is that we have learned the world model, then given a particular utility U, we should be able to understand, given the world model, if we take action A, what exactly is the expected utility. And then we should also be able to understand what exactly will be the uncertainty of this utility, given the world model. Then we can try to form a loss function or a reward function to try to maximize that. That will actually determine our actions to take. And then one can actually easily manipulate the whole setting to try to figure out new actions. Maybe it's very hard to take in reality, but it's very easy to simulate in the world model. I'm going to stop here. Look forward to more engaging discussions.
Great. Thank you.